No, you're not going to the bathroom. You're going to get a drink. There you go. All right. Note time. You guys need some paper? You guys okay?
Yeah, can we have paper?
Do you want plain white paper or do you want lined paper?
Line. Personally.
Me too. Yeah, I think line's probably better anyway. See? On the other side. Report. Here you go. And then I'll give you an exam question later.
Thank you.
I think we have everything we need now. Okay. And everyone hopefully should be settled. Okay. Cool. Let's talk about acids and bases then. So this. Got a pen? You want some of the felt markers?
Oh, like, actually, when we do that.
All right, cool. So today what I want to talk about is acids and bases. This is the final question you're going to get on your acids and bases exam. So it's very confusing that I'm saying the acids and bases exam and the acids and bases question. Okay? So just talking about the exam overall, there are 3 questions you're going to get. The first one is on atoms and ions, which we've already covered. And yes, 100% fact. So the first question is going to be atoms and ions and the ionic compounds. So talking about why ions form and why ionic compounds have their set ratios. The second question is going to be on rate of reactions. So talking about how we can change the temperature and what that's going to do to the speed of that reaction. And this is the last question that's going to be on acids and bases. With the acids and bases, first off, let's talk about what acids and bases are. So if I have something that is an acid, those are proton donors. So basically H+.
Okay.
So these things, when you mix it into water, will release the hydrogen ion.
Okay.
So for example, if I have hydrochloric acid, that's going to release a hydrogen ion. Or if I have sulfuric acid, that'll release 2 hydrogen ions. So it's the hydrogen ions that are going to be the important things that cause the acids to form. You guys have dealt with acids in everyday situations, such as in lemon juice or vinegar. Those are like everyday acids that you come across. So those things will be donating hydrogen ions to the water.
Oh,
yeah. The other type of thing that we deal with are bases. And they're basically the opposite of acids because the bases are proton acceptors.
So example would be like the water with acid.
Not so much water, but like we're thinking about something like sodium hydroxide. Is an example of an acid, or sorry, of a base. When this goes into water, it forms Na plus and OH minus. Now, what that OH does, that hydroxide, is that it will combine with a hydrogen ion and make water. So that's how it's accepting the proton. They remove the hydrogen ions, where these guys release hydrogen ions.
You get that?
Sure. All right. So when we're dealing with something like, for example, water, H2O, water can break apart into 2 ions. That is the hydrogen ion and the hydroxide, OH minus. Now, this is obviously an even ratio. You get 1 hydrogen ion and 1 hydroxide ion when it breaks apart. When other things break apart, they can sometimes release the hydrogen ion or they can release the hydroxide ion.
They can't do both.
Unlikely that they do both. For this one up here, when these guys break apart, you're going to get the hydrogen ion and the chloride ion. The hydrogen ion here is what makes something an acid.
Okay.
And then this sulfuric acid, when it breaks apart, you get SO4 2 minus. And again, that hydrogen ion that's being released is causing the acidic properties. So we just define acids as being proton donors, aka hydrogen donors. We call them protons because the hydrogen as an element on the periodic table just has the 1 proton in the center. in the nucleus, so we refer to them as proton. The bases do the opposite thing. So instead of releasing them, they accept them. So they take them in and they remove them from the liquid.
Yeah.
So an example would be sodium hydroxide. When sodium hydroxide breaks apart in water, you get the sodium ion and you get the hydroxide ion. The hydroxide ion is able to take a proton that's floating around in the water and take it off and remove it from the situation, forming water. So that's kind of the definition of how both of these guys are operating. Are we okay with that? Okay. Now, what we refer to help us kind of describe acids and bases is the pH scale. So this pH scale goes from 1 to 14, and in the middle is going to be 7. Now, what this pH scale is referring to is the concentration of hydrogen ions. Yeah, so actually the higher end, which is kind of counterintuitive, is the 1. The 1 is where you have a high H plus concentration, whereas 14 you have a low H plus concentration. 7 is when you have an equal amount. I say high H plus low OH, low H plus high OH. Okay, backtrack. So at a low pH, you have a high concentration of hydrogen ions, which is what makes something an acid. You have a low concentration of the OH ion, which is what makes something a base. On the flip side, for high pH, you have a low hydrogen concentration, and you have a high OH concentration, making it a strong base. If I'm at 7, the hydrogen concentration and the OH concentration are equal to each other. So that's neutral. Yeah. We indicate the differences using something called universal indicator, and that helps us kind of color code what we see happening. So if something is neutral, it will be a green color and just follows the rainbow. On the high end, I should say the low pH scale with the high acid, it'll be red. And then if it's really, really basic, then it's going to be purple. And it follows the rainbow scale. So if I was kind of there, it'd be blue. And then if I was going from this side, it would go yellow and then orange. That's kind of giving us a scale of what's going on. So we can use pH paper to tell something is basic or acidic. Are we okay with that so far? Okay. I'm trying to think what else. So there are other ways we can test if something is an acid or a base. I need to go through each one of them because they could all pop up on the exam. So the first one is, so this is just a scale that is showing either universal indicator or universal pH paper. So this one shows the full range of colors. There are other kinds of pH paper you can get. You can get red litmus. So the piece of paper is red, like that. Now this one will turn blue. But it'll only turn blue, whoops, sorry about that, if we have a basic solution. It will stay red if it's acid or if it's neutral. So that's another way we can tell what's going on. The next color is the blue litmus, and it works in exactly the opposite way. You start with blue, it goes to red. And again, similar sort of setup, it only turns red in acid.
And neutral.
No, neutral, it'll stay blue. So neutral will stay the color it is because it's not acidic or base. And that's in a base or neutral. Yeah? Good so far? Okay. The last one we got to talk about, it could potentially come up in your observations, and it is in the exam question that I have printed off, is when you mix an acid with a carbonate. So we have an acid plus some sort of metal carbonate. Or metal bicarbonate. Let me show you what that means. So an acid would be like hydrochloric acid, and a metal carbonate would be something like sodium carbonate. Okay. Metal carbonate would be sodium bicarbonate, which would just be like that. So it's the same kind of formula. The only difference is that I have a hydrogen instead of an extra sodium. So what happens when I mix these two things together is I'm going to get bubbles. Bubbles, which is your carbon dioxide, water, and your salt will form. So it's a good way for me to test if something is a carbonate, is that I'm going to expect bubbles coming out of it. All right, let me show you guys the exam question, and that will help kind of fill in some of the gaps that I have in the teacher. Go. There you go. So we're looking at page 4 to start with. There we go. All right. So we can see that they have 2 labeled colorless solutions. One is sodium. Oh, do you guys want the felt markers now? You don't have to match my color code. I'm not doing anything specific. I'm just picking colors at random. All right. So some things to keep in mind when we're looking at this is we have 2 unlabeled solutions. I've taken this from the 2020 exam. They have sodium hydrogen carbonate and sodium hydroxide. Both of these are bases, because I know hydroxides are a base, and I also know that hydrogen carbonates are a base and carbonates are a base. So all of that information tells me so far is that both of these things are bases. The thing I have to keep in mind, though, is I need to figure out which one is which. So I can't just use straight litmus paper because they're both going to turn red litmus blue. Yeah? So if I was to write down any observations, both of these would turn blue. This one would also turn blue. So that's not very helpful to me. But when I add it to sulfuric acid, I'm going to see a difference. If I add the sodium hydroxide to the acid, there's no bubbles that are going to form. This one will only form water and the salt. Whereas this one, because it has the carbonate component, this one will form bubbles. So that's how I'm going to distinguish the two. So this guy would have bubbles. This one would have no bubbles. All right, and then the explanation for each observation, you're just kind of writing out what you observe here. So you're going to say both of these will turn red litmus blue because they're both bases. And then you can then use one of your linking words that I love. However is a really good kind of linking word that shows comparison. So be mindful that on the assessments, a lot of the excellence points are if you have that comparison.
Sorry, which comparison?
So for excellence points, if they're giving you 2 things to compare, make sure you're using linking words that show that comparison. So both is an example of me saying that both, like comparing,
Similar?
yeah, they're similar. And then however is a good way for me to bridge to say these 2 things are different in this way. So, however, only sodium carbonate will form bubbles when added to sulfuric acid. And we can start explaining with more layers. It'd be like, this is because the sodium hydroxide only forms water and salt, whereas the sodium hydrogen carbonate and sulfuric acid will form water, salt, and the carbon dioxide. And the carbon dioxide's bubbles.
Right.
Do you need me to write that down, or you got that? It's like a gist.
Could you write that down?
Okay. So bubbles will be added to SO4. So you see I'm using the word whereas. The other thing to keep in mind when you're answering these questions is tie it back to the question. So instead of just saying carbonate, hydroxide, acid bases, a real general format, talk about the specific chemical they've given you.
Okay.
Because more so in the genetic standard than in the acids and bases, they do look for that tying back to the question for the excellence. Yeah, we're just gonna check out other people are doing while you guys get that last bit written down. Cool. So that one's done. All right, here, woohoo! Now they want you to do equations. The good news is we've already kind of covered it in the written answers, so we're just putting it in the equation format. So that kind of makes your life a little bit easier. So, in this first bit, the thing that we have to keep in mind with all these reactions is how to identify the products. So sulfuric acid, keep in mind that that's the going to turn to a sulfate, and you're taking the cation from this one to make the salt. So I would say that this is sodium sulfate. You see how I pulled the information through? Sodium, and then the sulfuric sulfate. Do you want me to write down the other ones in case they should pop up. If you had hydrochloric acid, HCl, so that would become, you'd have a chloride as your salt. This is the anion. So that's the negative ion. And then if you had nitric acid, that's the other one they can give you. That would become nitrate.
That's not just you, right?
Oh, what happened?
Is it hydrochloric?
Hydrochloric acid, nitric acid, and then sulfuric acid we just talked about. So sulfuric is the one that becomes a sulfate. Right. They will give you a table of ions, but you do need to know what it translates into. So since I looked over here, I'm taking the cation from this, which is the sodium. So when I say cation, I mean that it's the Na+. So we take the positive and the negative, put it together. So the base will give us the positive, and the acid will give us the negative.
Okay.
Yeah, I'll write that note. Base provides the positive ion, and acid provides the negative ion, which is our anion for the salt. Sorry, these notes are a little bit all over the show because the things occur to me as I'm teaching them. Okay. The other two things that we need to keep in mind is with all the neutralization reactions, you're going to get water.
And all of them?
All of them.
Okay.
And then the last thing you're going to get, in this case, because you have a carbonate, you will get carbon dioxide. So if I wanted to do the one on the bottom over here, the next reaction, it's basically the same setup. You have sodium and you have the sulfate, so sodium sulfate again. Plus water. There's no carbon dioxide in this example because this is a hydroxide.
Right.
Yeah. Cool. What else did I have to say about that? Can't roll it down. It doesn't matter the order that you put these guys in. So you could put water first, carbon dioxide, and then sodium sulfate. You can do carbon dioxide, water, sodium sulfate. Like the order of which you write them doesn't matter. What does matter is that's on the right side of the equation.
Okay.
So like it's on the after bit of the equation. Arrow. All right. Next thing I'm going to ask you to do is to translate this into a symbolic equation. So these are usually achieved points. The merit is the translation into the symbolic, and then the excellence is balancing it usually.
Okay.
I will show you guys the marking schedule at the end so you guys can know what to expect. So sodium hydrogen carbonate, NaHCO3. Again, use the table of ions to help you figure out what's what because they do give you the charge. Okay. So sodium is a +1 and the carbonate is -1. And since it's the same ratio, positive to negative, then they are the same. And then sulfuric acid, it's H2SO4.
We did this at the start for you, right?
We did. So hydrogen's a +1 ion, the sulfate is a -2, so I need 2 to 1.
Mm-hmm.
And then do my arrow, sodium sulfate, Na2SO4, because that's a +1, and that's a -2. H2O, CO2. Cool. Keep going. Okay. I'll do the bottom one as well, and then we'll balance it last. So same thing, that's sodium hydroxide, so that's NaOH, H2SO4, and Na2SO4, and H2O. Oh, and you guys, something that's great. If you read the question, you would notice that earlier, they've actually provided the formula.
Yeah.
So save you some time. The only formula that you had to figure out was this. Or did they give you sulfuric acid? They did. They gave you all the products.
Okay.
So all you had to do is figure out this one. Because water is H2O and carbon dioxide is CO2. That one should be like givens in your brain. All right, last step then is to balance it. So the main thing I'm going to use first to help me balance it is I'm going to check the sodiums because I see that this is 1 and that's 2. When it comes to balancing, you can only put numbers in the front, coefficients.
Right.
So I'm going to put a 2 in front of here to balance that out. And then I need to balance out my carbon dioxide and my water. So carbon dioxide, I see that there's 2 carbons now. There's only 1 on this side. So, so the small numbers on below tell us the quantity. So you see how that's Na, so there's 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens in this formula.
3 oxygens.
Now, when I look on this side of the equation and that side of the equation, I see that there's 1 and that one has 2. So I need to balance it, and I can only balance it by putting coefficients in front. I can't manipulate these numbers behind here because these numbers are referring to the ionic ratio. So since that's a 2, I'm putting a 2 in front. So now I have 2 sodiums and 2 sodiums on that side. Okay? Now that I've made that change with that 2 in front, I'm mindful that I have 2 carbons now. This side I only have 1. So I'm going to put a 2 in front of here. So it's like a sequence of events. If I do one thing, then I have to do the others as well. Again, I have 2 hydrogens here. I have 2 hydrogens here. So that's 4 total on this side. I only have 2 on this side. 2, 2, that's 4. That only has 2, so I'm putting a 2 in front there.
Right.
And now I think at this point I should double check it because I think I have everyone balanced. So 2 sodiums, 2 sodiums. I have 4 hydrogens on this side. I have 1 sulfur, 1 sulfur. I have, what is that, 6 oxygens plus another 4, that's 10 oxygens. Did I do my math right? 2 times 3 is 6, plus another 4, 10. Yep. All right, 4 on this side. 6, 7, 4, 5, 6, and then 7, 8, 9, 10. 10 on both sides. All right, it's balanced. We're done. Okay. This one's going to be easier to balance because it doesn't have the carbon dioxide to worry about. So 2, 1, 2 in front, and then 2 hydrogens, another 2 hydrogens, only 2 on this side, and that's 4, so 2 in front of there. So now I have 4 hydrogens and 4 hydrogens, and then when I check, I have 1 sulfur, 1 sulfur, 4 oxygens on that side, and, sorry, not 4, 6 oxygens on this side, and 6 oxygens on this side. So that's balanced. So just worry about neutralization equations because those are the only ones they'll give you on the assessment. They won't do like precipitation or the other ones that we talked about earlier this year. Cool. All right, looking at question 3, I just realized that I did not put this in color and it's kind of hard to see what you're supposed to see. Just keep in mind that this one here is a red and that one is an orange, which I think I might have given you both my orange. No, I didn't. That one's an orange. Do you need a red? Yeah. All right. So these two are both sulfuric acid beakers, but they are at different concentrations. We did a little bit of question 3 already. So unfortunately with this exam, they have done a little bit of Frankensteining, and they've mixed and matched the topic questions, which I think is really unfair for you guys. Usually they do it in a nice kind of orderly fashion where like, this is the atoms and ions question, this is the acids and bases question, this is the rate of reaction question. This time around, they've kind of moved things along, so you actually have a rate of reaction question and an acids and bases questions together, which is not very nice. Every so often, they're mean like that. All right, so both of these are the same acid, so it's important to note that, same acid. But we see that the acids are at different concentrations. One of them is 0.01, and one of them is 0.001. So basically what this means is that this one here is 10 times more concentrated.
Which one is?
This one here.
Okay.
Because you see how it's 0.01?
Yeah.
Whereas this one has an extra 0, or actually extra 2 zeros, I want to say. Yeah, 2 zeros. So it's 100 times more concentrated. Okay. So when they ask which beaker is the most concentrated acid solution, it'd be beaker A. All right. This one wants you to explain why the different solutions have different colors and link it to the concentration of hydrogen ions and hydroxide ions and what the pH would be for each solution. So that would be relating to what we've been talking about over here with the color differences. So since this one is red, it's going to have a higher concentration of the hydrogen ions, a low concentration of the hydroxide concentration. The beaker B will also have hydrogen ions, but it's going to be 100 times less in comparison to that one. So that's why there's different color changes and also different pH numbers. So this one I would expect to be about pH 1 or 2. This one would probably be like 3 or 4 because it's closer to the 7.
Yeah.
So that's kind of the thing that you're thinking about with that. I'm going to save us some time and not write it all down, but I'll show you guys what the marking schedule looks like so you have an idea. But that's the idea with that question there. And then the last question that I wanted to show you, I think we started talking about previously because it had collision theory. So this is the rate of reaction stuff. This is what I'm saying about how like this one was not a nice question. They've mushed them together. But here they've given you the copper oxide and copper oxide and sulfuric acid being mixed together. I just want to talk about this reaction in particular because it's a very common one they like to give. So basically what they do is they take the copper oxide, which is a black solid, and they add sulfuric acid and they heat it. When they heat those two things together, it will make a blue color after the reaction is done, and you can filter out any remaining extra copper oxide. So we're just going to ignore that there, so that way I can write the notes. So you have H2SO4 plus CuO, that's copper oxide. So this is another example of a neutralization reaction. And the reason why it's also a neutralization reaction is because we're getting rid of that acid component. So it's neutralizing it. So when these two guys come together, one of the products is going to be the copper sulfate, which I talked about up here. CuSO4. And then what you have left over is the hydrogens and the oxygen, which will make water. H2O. So I just wanted to point that out in case it comes up, because it's a very common question. And so the blue color is that copper sulfate. So yeah, sometimes they're a little nasty.
Collision theory is where the particles actually.
Yeah, so in this case with the collision theory, I'm just grabbing a different color. They're talking about heat because they have warm sulfuric acid versus cold sulfuric acid. So this is relating to the temperature. So if you guys remember when we did this, I think it was a couple weeks ago. I think it was 2 weeks ago. We talked about how for collision theory to work, the particles need to meet and collide, and they have to collide with enough energy. So those are the two requirements in order to have a successful collision. In this case, because we're increasing the temperature, our particles are moving faster, so they're more likely to collide, and they're more likely to collide with enough energy to have a chemical reaction. The thing to keep in mind when you're talking about collision theory is make sure you talk about it within a time frame, so per second or per unit time, because we're saying there's just saying there's more collisions isn't sufficient because there's always going to be collisions, but the fact that there's more collisions per second, so in a time frame, the collisions are more likely. Then that
should be the mistake constructed by saying per second.
Yeah, you should definitely say per second.
Okay.
Yeah, I'm just saying, yes, there are more collisions, but you need to specify that the collisions are happening more frequently in a second, in a set unit of time.
Well, no.
Does that make sense?
Yeah.
Okay, let me pull up the marking schedule so you can see what that looks like. Oh, now I gotta find it. Yeah. Wait, are you talking about my questions or?
The first two questions that we went over, I think I was there for one of them.
Did I add you to my Google Classroom? I can't remember now. I don't think I have. Let me add you to my Google.
Email or something?
Huh?
You need my email?
No. I just looked you up on the system in it. So these are the other two questions that I did. Yeah, these are the other two that I've done.
Yeah. Okay.
And I should have recordings on there. Yeah. I don't know. That should be deleted. Sorry, I forgot to delete that. That's the last question. There's the marking schedule. So we want to go to question number 2. So 2, or was it 1? Oh, here's question 1. Yeah. You see how this one they're talking about the observations, and then they're doing that compare and contrast of the acids and the bases. Sorry, the two different bases. And then here are your equations. And so the breakdown of the points. So achieve point, 1 row of the table correct or 1 column of the table correct. So what they were talking about was if you had 1 row correct or 1 column correct. For the achieved, explains 1 observations, can't be repeated in the table. The red litmus turns blue in a base is okay, but if it's already in your table, we can't double count it as points.
Oh, okay.
M3, complete the table with 1 observation. Oh, that's pretty easy. That's not a lot for a merit point. And then the excellence point was explaining the identification. Yeah. And you see, this is what I'm saying about the excellence point. Correct balanced equation. And they only needed 1.
Okay.
You got 2 chances of it. And this one here one symbolic equation, but not balanced. You get 2 chances to do that. But you're only going to get it count once. So that was that one. See? Then we'll look at question 3. Yeah. So that first one that we were talking about with the copper oxide and the sulfuric acid, identifying it as a neutralization reaction was just an achieve point, which makes sense because there's only one line there and there's no explanation. And then this one here was talking about the collision theory. So you get another collision theory. I think it's actually 2 collision theories in this question, in this exam. From memory? Yeah, there's another collision theory that we talked about last week, which is talking about surface area.
Oh, yeah.
So there's 2 collision theory questions. All right, make sense?
Yeah.
Okay, cool. And that's everything for acids and bases.